We usually think of numbers as stepping stones. 1, 2, 3. Clean, predictable, evenly spaced. But zoom in, and that rigid grid shatters. The spaces between those whole numbers contain an infinitely dense, chaotic fractal of fractions and decimals. To navigate this, mathematicians categorize these spaces into sets. We start with the integers, represented by z. Those sit inside the rational numbers, q, which can be written as fractions. And encompassing all of it is the continuous, infinite spectrum of the real numbers, r. Analyzing these sets rigorously requires viewing numbers as structural components with specific physical behaviors. The infinite expanse of the real number line appears boundless, but it is strictly governed by the microscopic behavior of simple positive integers. We can map this control system by looking at two specific mechanical engines. The first engine is the rules of divisibility. The second engine dictates how numbers are built through multiplicative composition. By unpacking these two theorems, we can compute highest common factors, prove why certain numbers can never be written as fractions, and predict the exact infinite behavior of a decimal sequence without calculating it. Divisibility and composition provide the mechanical constraints that define how integers interact within the broader real number system. In higher mathematics, division is a strict algorithm used to define spatial boundaries. This is Euclid's division algorithm. It states that any positive integer a can be divided by another positive integer b, producing a quotient q and a remainder r. The equation is simply a equals b times q plus r. This relationship functions as a physical packing problem. We have a large quantity, a, and a smaller base unit, b. The algorithm asks how many complete b units can we pack into the space of a. That total count of b blocks is our quotient, q. Unless b fits perfectly, there will be empty space left over at the end of the line. That leftover gap is the remainder, r. The entire algorithm hinges on one non-negotiable geometric constraint. The leftover gap r must be strictly shorter than a single b block. If it wasn't, you could pack another b into the space. This spatial logic provides a reliable method to compute the highest common factor, or HCF, of any two positive integers. By feeding the remainder back into the algorithm as the new divisor, we recursively shrink the boundaries. We repeat this packing process into smaller and smaller gaps until a block fits perfectly with zero remainder. The final block that fits is the HCF. Euclid's algorithm transforms the concept of division into a tool for defining the absolute limits and shared proportions of integers. If Euclid's algorithm breaks numbers down by subtracting blocks of space, our second engine builds them up through multiplication. This is the fundamental theorem of arithmetic. The theorem states that every composite number is constructed by multiplying a specific fixed combination of base mathematical units. Take a composite number and fracture it. It splits into a branching tree of smaller interconnected factors. Those branches continue to split until they hit irreducible dead ends. These final nodes are the prime numbers, the atomic, indivisible elements of integer mathematics. The most critical property of this theorem is uniqueness. Every composite number possesses exactly one prime factorization sequence. The order in which you multiply them doesn't matter. The exact set of primes required to build that specific number is absolute. Prime factorization reveals the internal composition of a number, providing a unique structural signature that distinguishes one integer from every other. We apply this diagnostic tool to evaluate the nature of roots like the square root of 2, 3, and 5. We will use the absolute uniqueness of prime composition to prove that these numbers can never be written as simple fractions. The logical framework here is a proof by contradiction. We start by assuming the exact opposite of what we want to prove, and follow the logic until it breaks. Assume the square root of 2 is rational. That means it equals some integer p divided by some integer q. To remove the square root and isolate the integers, we square both sides and rearrange the terms. This leaves us with a clean equation. 2 times q squared equals p squared. Now analyze both sides of this new integer equation exclusively through their prime factorization. Look at the right side, p squared. Because p is squared, every prime factor it contains appears twice. Therefore, its prime factorization must contain an even total number of prime factors. Now look at the left side, 2 times q squared. The q squared also contains an even number of factors. However, multiplying it by that solitary extra 2 adds exactly one more prime to the pile, creating an odd total number of prime factors. Here is the impossible contradiction. The fundamental theorem guarantees unique prime factorization. A single whole number cannot have an even number of prime factors on the right side of an equation and an odd number on the left. This paradox forces us to reject the initial assumption. Numbers like the square root of 2 cannot be written as fractions, proving that irrational numbers represent a structural break from the rational number system. These integer rules govern how fractions resolve into decimal sequences. How can inspecting just 1/2 of a fraction definitively predict the behavior of an infinite chain of decimals? Take a fraction, p over q. We ignore the numerator, directing all focus to the denominator, q. A prime scanner breaks it into its constituent prime nodes. If it detects only nodes 2 and 5, the decimal cleanly terminates. Any other prime loops infinitely. The underlying logic for this is dictated by our base 10 number system. The number 10 is exclusively composed of the prime factors 2 and 5. Therefore, any power of 10 is also built strictly from those same primes. Introducing a prime factor like 3 or 7 prevents the fraction from dividing cleanly into base 10. This traps the calculation in an inescapable repeating remainder loop. By isolating the prime factors of the denominator, we can determine the exact pattern of a decimal expansion without ever performing the division. Imagine taking any physical object in the universe and breaking it down until you hit the smallest possible component. Numbers behave exactly the same way. The infinite sea of mathematics is built from indivisible, microscopic parts. We call these numerical atoms prime numbers. Because they can only be divided by 1 and themselves, they cannot be broken down any further. They are the rigid foundation of all integer mathematics. Mathematicians have recognized this structural reality for millennia. You can trace the attempt to formalize how these primes behave all the way back to ancient texts like Euclid's Elements. Today, we define this behavior with Theorem 1.1, the fundamental theorem of arithmetic. This theorem serves as the foundational rulebook for exactly how prime atoms combine to form every other number. The first part of this rulebook guarantees existence. It states that every composite number, no matter how large or complex, can be successfully shattered into a product of primes. Let's test this by dismantling a larger composite number, like 32,760. If we start dividing, the calculation cascades downward. We can pull out a 2, then another 2, then a 3, and so on. We keep splitting the branches until we are left with nothing but a scattered collection of unbreakable prime nodes. The second part of the theorem guarantees uniqueness. If we gather all those scattered primes and arrange them in strict ascending order, we compress them into a precise algebraic string, 2 cubed times 3 squared times 5 times 7 times 13. This specific sequence is this number's unique prime signature. There is no other combination of prime numbers in the universe that will multiply together to equal 32,760. This uniqueness provides a predictable model for every integer. Once we have a number's prime signature, we understand its properties regardless of its scale. If a sequence of numbers goes on forever, how do you prove that a specific outcome will never happen? You obviously cannot manually check every number if the list has no end. Let's look at the infinite powers of 4. 4, 16, 64, 256, and so on, defined algebraically as 4 to the power of n. We want to know, if we calculate this forever, will we ever find a number that ends in a 0? To answer this without calculating infinite numbers, we just check the structural rules. For any integer to end in a 0, it must be perfectly divisible by 10, and the prime signature of 10 is simple. It requires exactly 2 ingredients, the prime number 2 multiplied by the prime number 5. Now, let's look at the underlying structure of our sequence. The base number 4 breaks down into 2 squared, so 4 to the power of n is exactly the same as 2 to the power of 2n. The only prime factor present in this entire infinite sequence is 2. The required 5 is entirely missing. Because the fundamental theorem of arithmetic guarantees that factorizations are unique, a prime factor of 5 cannot spontaneously generate later in the calculation. By checking the prime architecture, we reach a definitive conclusion. Since the combination of 2 and 5 is physically impossible to construct here, the sequence of 4 to the end will never end in 0. We can apply this exact same structural logic to determine exactly how 2 separate numbers interact. Let's take 2 common integers, 6 and 20. We begin by extracting their exact prime signatures. 6 is 2 to the first power times 3 to the first power. 20 is 2 squared times 5 to the first power. To find the highest common factor, or HCF, we are looking for the maximum structural intersection between these two blueprints. We want to identify exactly which pieces they share. The rule is to locate the prime factors present in both numbers, in this case only the 2, and extract the smallest power. 2 to the first power is 2, so our highest common factor is exactly 2. The least common multiple, the LCM, is the opposite approach. It represents the smallest boundary that can perfectly enclose the full prime structures of both original numbers simultaneously. Here we take every prime factor present across both signatures, 2, 3, and 5, and we isolate the greatest power of each. That gives us 2 squared, 3 to the first, and 5 to the first. When we multiply those maximum powers together, we get our least common multiple, 60. Calculating HCF and LCM is a systematic method for placing the internal prime structures of 2 integers side by side, measuring exactly where they overlap and where they diverge. This direct comparison of prime structures yields a clean mathematical symmetry. This identity states, multiplying the highest common factor by the least common multiple equals the product of the original 2 base numbers. Testing this, we take our HCF, 2 to the first power, and multiply it by our LCM, 2 squared times 3 times 5. The prime factorization exposes the mechanics. Since the HCF extracted minimum powers and the LCM extracted maximum powers, every component is accounted for. Rearranging these primes, they form 2 to the first times 3 to the first, alongside 2 squared times 5 to the first. We have physically relocated the exact same mathematical atoms without losing or duplicating a single piece. The equation works because the prime components of the HCF and LCM are literally just the reassembled parts of 6 and 20. This is the utility of analyzing prime factors. We move past memorized equations and observe the actual mechanics driving the outcomes. The fundamental theorem of arithmetic proves that the behavior of integers is dictated entirely by their smallest parts. Beneath the scale of infinite numbers lies a perfectly strict, orderly, and entirely predictable prime architecture. You finish a math test, drop your pencil, and stare at your final answers. You hope they're right, but hoping isn't knowing. That gap between finishing a problem and knowing it's correct is where test anxiety lives. We can eliminate that gap. Today, we use the prime factorization method to extract the highest common factor and least common multiple of any given numbers. We will apply a specific verification formula that acts as a mathematical audit. It proves your final answer is correct before you ever hand in the paper. To execute this, you only need two basic tools: an understanding of prime numbers and how to write them using exponent notation. By combining prime factorization with a mathematical proof, we stop relying on estimation. We shift your mindset from hoping for a passing grade to guaranteeing one. Let's start the process with two standard numbers straight from the curriculum: 6 and 20. First, we break 6 down into its prime building blocks: 2 to the power of 1 times 3 to the power of 1. Next, 20 branches out into 2 squared times 5 to the power of 1. Now align these two factorizations vertically. Translating raw numbers into this standardized, stacked format of prime exponents is the essential foundation. It organizes the data so we can reliably pull both the HCF and LCM directly from the structure. The rule for isolating the highest common factor requires filtering. You must locate only the prime factors that both numbers share and take the smallest power of those shared primes. Looking at our stacked equations, we scan the columns vertically. There is exactly one shared prime base, the number 2. We compare their exponents, the 1 and the 2, and select the smallest, pulling the 2 to the power of 1 down. The 3 and 5 are ignored. The HCF is a problem of strict limitations. It isolates only the minimum ingredients required to build what both original numbers have in common. Here, our HCF is simply 2. The least common multiple requires the opposite approach. We are no longer filtering. We must take the greatest power of every single prime factor present across either number. Returning to our stacked diagram, we identify all unique prime bases, 2, 3, and 5. We grab the highest exponent for our shared base, 2 squared, and bring it down alongside our unshared bases. Multiplying these highest powers together equals a final value of 60. The LCM is a problem of maximum capacity. It gathers the total ingredients needed to encompass the multiples of both original numbers. This brings us to the two-number verification formula. For any positive integers a and b, the product of their HCF and LCM equals the product of the original two numbers. We can plug our values into this scale. On the left, we drop our HCF and LCM, 2 times 60. On the right are original numbers, 6 times 20. Both sides equal 120. The scale balances perfectly, proving our initial prime extractions are correct. You can also leverage this formula in reverse. If you already know the HCF and your starting numbers, you can easily divide to locate a massive LCM without drawing complex factor trees. Mastering this formula changes math from a game of guessing into a system of proof. Stop right here. Before you carry this logic into your exam, there is a limitation you need to know. Look at a three-number sequence from the textbook: 6, 72, and 120. You can extract their HCF as 6 and their LCM as 360. But if you multiply 6, 72, and 120 together, the result does not equal the product of their HCF and LCM. The verification formula is an exclusive mathematical property. It rigidly belongs to two-number pairings, and it fails the moment a third variable enters the equation. Let's review the pillars. Stack your crime equations. Find the smallest powers of shared bases for the HCF and capture the greatest powers of all bases for the LCM. Once you have those results, apply the verification formula. You now have the ability to prove your own work. Practical fluency requires both finding the result and possessing the logical tools to prove that result is correct. We perceive a line as a smooth, unbroken progression, but when we attempt to map this line using only the numbers we use for counting, the continuum appears to break apart. On the number line between 1 and 2, every point seems like it should have a specific, nameable address. Consider the position roughly at 1.414, the square root of 2. We can zoom in on this coordinate forever, adding more decimals to get closer to its true location. We try to define this point using a rational fraction, a ratio of two integers, p over q. We want this to lock onto the exact coordinate, but regardless of the integers, it only approaches the target. It never perfectly lands. This point is an irrational number. It is a coordinate on the line that simply cannot be expressed as a ratio of two whole integers. Since there are an infinite number of fractions to choose from, we have to ask how we can be certain that a perfect ratio for the square root of 2 doesn't exist somewhere in that infinity. To find the answer, we have to look away from the continuous line and look toward the finite, discrete building blocks of the integers themselves. The proof rests on how prime numbers combine to form every other integer, a concept known as the fundamental theorem of arithmetic. Every integer has a unique structure. It is built from prime numbers, which are the indivisible units of arithmetic. We can deconstruct any integer into these parts. For example, look at 96 and 404. 96 is composed of 5 2's and a 3. 404 is composed of 2 2's and a 101. These prime bases and their exponents represent the unique code of the number. To find the highest common factor, we identify the shared prime bases with the smallest exponents. In this case, both numbers share 2 2's, making their HCF 4. For the lowest common multiple, we take all the distinct prime bases at their greatest exponents, 2 to the 5th, 3, and 101. For any two numbers, the product of their HCF and LCM will always equal the product of the two original numbers. This relationship is specific. It changes when we add a third number, like 6, 72, and 120, because the distribution of primes becomes more complex. These prime factorizations aren't just a shorthand. They are the rules that determine how numbers can be divided or combined. To prove the square root of 2 is irrational, we use a specific property of prime factorization. Theorem 1.2 states that if a prime number p divides an integer squared, a squared, then p must also divide the original integer, a. Think of any integer a as a simple string of prime factors multiplied together. Squaring that number duplicates every prime in the string. If we had 1 3 and 1 5, we now have 2 3's and 2 5's. Squaring changes the quantity of the primes, but it cannot introduce a prime that wasn't there to begin with. This means if a new prime is not in the original integer a, it cannot divide the squared version, a squared. So, if a prime exists within a squared number, it must have existed in the original root. Now we apply this to the square root of 2. We want to show it can never be a rational fraction. We'll use a proof by contradiction. We start by assuming the opposite, that the square root of 2 is rational. We assume square root of 2 can be written as a fraction and set it equal to p over q. We also assume this fraction is fully simplified. This means p and q are coprime. They share no common prime factors. If we square both sides of the equation, the root disappears, leaving us with 2 equals p squared over q squared. We multiply both sides by q squared to get our test equation. 2 times q squared equals p squared. Since p squared is equal to 2 times an integer, p squared is even. This means it is divisible by the prime number 2. This is where we use our theorem. If 2 divides the square, p squared, then 2 must also divide the root, p. We have just discovered that the prime 2 is a part of the structure of our numerator, p. If p is divisible by 2, we can rewrite p as 2 times some other integer, which we'll call c. Now we substitute 2c back into our equation where the p was. When we square that term, 2 times q squared becomes 4 times c squared. Dividing both sides by 2 reveals that q squared also equals 2 times an integer. This means q squared is also an even number, divisible by the prime 2. Applying the theorem one more time, if 2 divides q squared, then 2 must divide the denominator, q. Here is the problem. we have shown that both p and q are divisible by 2, but we started with a requirement that the fraction was fully simplified and the numbers shared no common factors. This result contradicts our starting point. Because this contradiction exists, the original assumption must be false. The square root of 2 cannot be rational. By following the rules of how integers are built, we've proven that the number line contains values that no fraction can ever reach. The universe of numbers feels infinite. We can zoom endlessly forward, discovering new layers of scale in every direction. This basic number line gives us our mathematical framework, the integers, 0, 1, 2, 3. Between these solid anchors, we pack in the fractions. Divide any whole number by another, and you get a rational number, filling the spaces until the line looks completely solid. But if we zoom in close enough, right between 1.4 and 1.5, that solid continuum breaks. There is a specific, perfectly empty gap right where the square root of 2 belongs. This gap exists because the square root of 2 is irrational. That means it absolutely cannot be written as a clean fraction, p over q, where both are integers. We cannot prove this by simply calculating its decimal expansion. You could compute the square root of 2 to 1 billion decimal places, but because you can never reach infinity, you can never prove it won't eventually settle into a repeating fractional pattern. To definitively prove this gap exists, we have to abandon calculation entirely. We have to rely on pure structural logic, using a method called proof by contradiction. Every single whole number in our universe has a hidden internal architecture, built entirely from these unbreakable mathematical blocks. We call these foundational blocks prime numbers, 2, 3, 5, 7, and so on. This brings us to the fundamental theorem of arithmetic. If you take the number 15, it splits perfectly into 2 distinct prime blocks, a 3 and a 5. Number 12 splits into its own unique chain, a 2, another 2, and a 3. Because prime numbers cannot be broken down any further, this specific sequence is the absolute only way to construct that integer. If you know a number's prime building blocks, you know its inescapable mathematical DNA. Look at this visual model of a generic integer, which we will call a. We don't know its exact value, but we know it is built from a specific connected chain of prime blocks. Let's perform a simple mathematical action, squaring this integer to get a squared. Squaring an integer simply means multiplying that exact same string of prime factors by itself. Notice the resulting pool of blocks. We have 0 new prime numbers. We've merely doubled the exact set of originals. Now imagine a scenario where we find a prime number, let's call it p, that perfectly divides into this new a squared pool. Because p is prime, it cannot be formed by combining smaller pieces. It must perfectly match a block already in that pool. Since the a squared pool is just 2 identical copies of the original a string, block p absolutely exists in the original a pool. This establishes a formal mathematical law known as Theorem 1.2. If a prime number divides a squared, it absolutely must divide a. Squaring a number cannot miraculously generate a prime factor that wasn't already present in its foundation. We will use that law to set a trap. Using proof by contradiction, we assume the impossible and watch the math shatter its own rules. Look at this equation. We will assume, entirely against reality, that the square root of 2 is perfectly rational. It equals an integer a divided by an integer b. Any valid fraction can be fully simplified. When simplified, top integer a and bottom integer b become coprime, sharing 0 common prime factors, just as 4 over 6 reduces to 2 over 3 and locks. This coprime condition is our unbreakable law. A and b share no prime factors. If we prove that a and b actually do share a hidden factor, our simplified fraction is a lie, and the entire premise collapses. Let's run the algebra. First, we multiply both sides by b to clear the fraction. b times the square root of 2 equals a. Next, we square both sides to generate whole numbers. We get 2 times b squared equals a squared. Read the output. Because a squared equals 2 times some other integer, it must be an even number. The prime number 2 divides a squared. By theorem 1.2, 2 divides the original a. Being even, a can be rewritten as 2 times integer c. Substituting this back, 2b squared equals 2c squared. Simplifying, 2b squared equals 4c squared. Dividing by 2 leaves b squared equals 2c squared. The pattern repeats. Now b squared is equal to 2 times something. That means b squared is even. We apply theorem 1.2 a second time. If 2 divides b squared, then 2 must divide b. The algebra has run flawlessly, and it has dictated that both a and b are even multiples of 2. Pacing slows for emphasis. We bring these two mathematical conclusions face to face with the strict rule we set at the start. A and b share a factor of 2, but we defined them as coprime, sharing no factors. They cannot coexist. Because our algebra is flawless, the original assumption is the source of this broken reality. The premise was a lie. The square root of 2 cannot be written as a fraction. It is irrational. This exact same logical engine breaks the fractions for the square root of any prime number. Try it with the square root of 3, and the math forces a and b to both be divisible by 3, creating the exact same paradox. Irrational numbers are not just random mathematical glitches. They are absolute structural necessities, perfectly guaranteed by the bedrock rules of prime factorization. In mathematics, the boundary of a rational number is strict. If a number is rational, it can be expressed as a fraction of two numbers, an a divided by a b. There is a crucial constraint to this definition. The top and bottom values, a and b, must be perfect whole integers. We find values that challenge this rigid system in the space between our whole numbers. On a number line, square roots like the root of 2 and the root of 3 expand into decimal strings that never end and never repeat. While it seems intuitive that these infinite decimals cannot be packaged into a simple fraction, intuition is not proof. To establish a mathematical truth, we cannot simply test every possible fraction. We need a mechanism of absolute proof. The logical tool for this is reductio ad absurdum, or proof by contradiction. To prove that something is impossible, we start by assuming the exact opposite. We temporarily treat the impossible claim as if it were factually true. We then apply the strict rules of arithmetic to that assumption and follow the equations until the system inevitably reaches a paradox. We will apply this framework to our roots. By forcing the square root of 2 to equal a fraction, a over b, we can observe how the underlying algebra reacts. Breaking a false assumption from the inside out ultimately reveals why the original premise was completely mathematically impossible. Assume the square root of 2 exactly equals integer a divided by integer b. They are coprime, sharing no common factors other than 1. Squaring both sides removes the root. Rearranging shows 2 times b squared equals a squared. Because b squared is multiplied by 2, the result is an even number. Since it equals a squared must also be even. By assuming the root of 2 is a rational fraction, we have forced the numerator to behave as an even square. We must now address a specific property of prime numbers. Theorem 1.2 states if a prime divides a squared integer, it divides the base integer. Since prime 2 divides the area a squared, it must divide the base length a. We can thus define a as 2 times integer c. This relationship between the square and its root allows us to re-examine the other side of our original equation. Returning to the equation, 2b squared equals a squared, we substitute our new definition of a. Expanding the right side, 2c squared becomes 4c squared. Dividing both sides by 2 leaves b squared equals 2c squared. The algebra now dictates that b squared is also a multiple of 2. Following the rule, if b squared is even, base b must be even. The algebra proves both a and b are even, sharing a factor of 2. This directly violates our assumption that they were coprime, sharing no factors. Because following the rules of rational numbers led to a logical impossibility, the system rejects the root of 2 as a fraction. It is irrational. This process is not unique to the number 2. We can run the square root of 3 through the same logic. Squaring both sides shows that a squared equals 3b squared, making a divisible by the prime number 3. Substituting this back into the equation forces b to also be divisible by 3, creating the same coprime contradiction. The square roots of prime numbers are bound by this systemic law. They cannot exist as simple fractions. We can also observe what happens when irrational values interact with standard rational numbers. Consider a compound expression, 5 minus the root of 3. Assuming this expression is rational and isolating the root, we can check for consistency. This leaves us with the square root of 3 on one side and 5 minus a rational fraction on the other. This creates a mismatch. Subtracting a rational fraction from an integer will always result in a rational value, yet we have already proven the root of 3 is irrational. Multiplying or dividing by irrationals produces the same result. A rational output can never balance an irrational input. Irrationality is mathematically dominant. It cannot be canceled out or balanced by standard rational arithmetic. These proofs are made possible by the underlying structure of all integers. This is the domain of the fundamental theorem of arithmetic. Every composite number is built from a unique set of prime factors, a specific mathematical identity. Because whole numbers have this rigid internal architecture, the behavior of their ratios is strictly limited. The proof demonstrates that when we calculate the root of a prime, we are finding a value that simply cannot be constructed from the fixed building blocks of our whole number system. If you break any whole number down to its absolute base, you find a strict, unalterable genetic code. Mathematicians call this code the fundamental theorem of arithmetic. The theorem states a rigid law. Every composite number can be broken apart into a product of prime numbers. This diagram illustrates that rule in action. The number 30 splits exactly into the prime blocks 2, 3, and 5. The crucial detail is uniqueness. Apart from the order you write them in, there is exactly one valid combination of primes per number. If you try constructing 30 using a 7 or 11, it is physically impossible. The pieces will not fit. This factorization acts as a rigid structural constraint. It dictates the mathematical limits of any calculation by defining the internal composition of every integer. We can apply this exact prime constraint to solve two distinct high-level mathematical problems. First, we will prove with absolute certainty that a specific number cannot exist as a fraction, doing so entirely without calculating a single infinite decimal. Second, we will use it to audit the chaotic overlaps of 3 intersecting datasets. Both solutions rely entirely on the fact that the fundamental theorem of arithmetic serves as the physical architecture of the number line. To solve the first problem, we need to look at perfect squares, but strictly through the lens of their prime factors. Squaring variable a simply means taking the exact prime blocks inside and perfectly duplicating them. This strict boundary rule means 0 new primes can spontaneously generate during exact cloning. Thus, finding a specific prime block inside a squared variable guarantees it already existed inside the original root. We can formalize this logic into a powerful mathematical lemma. If a prime number p divides a squared, then p must also divide a. A square number is merely a genetic clone of its root. The prime factors building it are entirely locked in place. We will now apply that lemma to a classic problem, proving that the square root of 5 is strictly irrational. We prove this by contradiction. We assume the square root of 5 is a perfectly simple fraction, and watch the math physically break under its own structural rules. We assume root 5 equals fraction a over b, locked in simplest possible form. Rearranging clears the root. 5b squared equals a squared. The left is explicitly multiplied by 5. To balance, the right side, a squared, must also be a multiple of 5. Applying our lemma, if 5 divides a squared, the prime block 5 must live inside variable a. Substituting a with 5c simplifies the equation to b squared equals 5c squared. Now b squared is a multiple of 5, proving prime 5 also lives inside variable b. We have now isolated the prime block 5 inside both a and b. Remember our initial assumption. We defined a and b as sharing absolutely no common prime blocks. The mathematical structure has contradicted itself. The constraints of the fundamental theorem of arithmetic forced this mathematical collapse. Because the genetic code of the numbers breaks under these conditions, the square root of 5 cannot exist as a rational fraction. Irrationality is a structural impossibility enforced by the unbreakable laws of prime constraint. The infinite decimal points we see are merely a symptom of this rigid prime architecture. That same constraint governs how complex variables interact when we analyze intersecting datasets. When dealing with two numbers, p and q, there is an elegant algebraic rule. The lowest common multiple, multiplied by the highest common factor, equals the product of p and q. Look at this equation on screen. It is a common mistake to assume this rule scales safely up to 3 variables. It fails immediately. The mechanical failure happens at the prime level. Multiplying 3 numbers together does not perfectly align their primes. It blindly overstacks them. This Venn diagram models variables p, q, and r as massive overlapping spaces. Simple multiplication mathematically overcounts the specific prime blocks trapped in those overlapping intersections. To correct this, the formula for 3 variables introduces a set of denominators. Each term in the denominator represents a pairwise overlap, p and q, q and r, or p and r. Dividing by these specific common factors strips away the double-counted prime blocks, leaving only the unique, balanced structure of the variables. Introducing a third variable shatters basic equations because it creates hidden, intersecting prime dimensions that demand strict accounting. Let's pull back and align these two concepts. Look at this split screen. On one side, we proved a root stretches into infinity. On the other, we balanced the overlaps of a 3-variable dataset. The underlying engine making both of these logical feats possible is the exact same mechanism. Unique prime factorization is the definitive boundary condition of mathematics. It acts as an absolute governor. It dictates what rational systems can be built and strictly enforces how complex systems must interact. This grid illustrates the true nature of prime factorization. It is advanced logical architecture. Every number is a specific, engineered point within this unbreakable field. Mastering these prime building blocks provides the key to navigating the structural blueprint that governs the entire logical universe.